name is Dana Golden, and today we're going to talk about the bidding behavior and the characteristic of energy storage systems. So, energy storage systems can be divided into electrochemical energy storage systems, mechanical energy storage systems, electromagnetic energy storage systems, and thermal energy storage systems. Electrochemical can be divided into thermochemical, battery, fuel cell. This is mainly hydrogen. Battery, we'll talk about, is several metals together that store electricity. Mechanical is potential, compressed air, energy storage, pumped hydroelectric storage, and kinetic in terms of flywheel. And then magnetic includes superconducting magnetic energy storage, electrostatic capacitor and supercapacitors, and thermal low temperature and high temperature storage. So you can create thermal storage both with low temperature systems and high temperature systems. So how does pumped hydroelectric storage work? It's large scale energy storage technology that uses gravitational potential energy. This is the traditional form of energy storage that we've seen in the grid. How does it work? During times of low electricity demand and low prices, water is pumped from a lower reservoir to an upper reservoir. And during peak demand, water flows back through the turbines to generate electricity. So you're storing electricity during periods of low demand, low prices, and you're letting, so you're storing water and energy in the form of higher water in terms when prices are low, and then when prices are high, you let the water go. It flows back to the current turbines and generates electricity. Obviously, this provides grid stability and flexibility, and it can be very quick to respond to demand changes. And it's highly efficient, not as efficient as some of the other practices we'll talk about today, but has a round trip efficiency of 78%. It requires very specific geographic conditions. You have to have the elevation difference. There's a high upfront cost and a long construction time. And then, of course, we can talk about batteries. I think I've shown a similar picture of this before in a battery, which is, I think, what most people think about when they think about energy storage. You have discharge. We have electrons moving across from positive to negative. You have the cathode, which is an aluminum current collector, and a copper current collector of an electrode separated by a separator, and then an electrolyte. And you have lithium ion metal oxides here, and then lithium ion on the other side. And then when you're discharging, you're moving here from the negative to positive side. So you're moving from the copper current collector over here. And then when you're discharging, when you're charging, you're moving away. You're moving from the cathode to the anode. So from the lithium ion metal oxides to the copper current collector. So charging, you're moving this way and storing the electricity, and then discharging, you're moving this way. You're moving from the anode to the cathode when you're discharging, and you're moving from the cathode to the anode when you're charging. And this is made up of aluminum current collectors, copper current collectors, and lithium ion metals. So types of batteries, lithium ion is the most common, sodium sulfur. Used to be very common, stopping because of some of the disadvantages, nickel cadmium. Vanadium redox, or a flow battery, is becoming very popular, is an increasingly common and increasingly exciting technology. And then, of course, you have zinc bromine. So lithium ion, widely used in grid scale and portable applications, high energy density and efficiency. You have sodium sulfur, which operate at high temperatures and are suitable for long duration energy storage. One thing I'll mention about sodium sulfur is they're pretty susceptible to memory effects. Basically, the more you use the battery, if you don't fully discharge it, the battery can lose some of its storage and it can depreciate faster. Next, we have nickel cadmium, which is robust and reliable with a long lifespan and can tolerate extreme temperature variations. This is good for energy storage in pretty extreme climate and for use cases when you need it to be there for a long time. Then we have vanadium redox flow batteries, which store electricity in liquid electrolytes and are scalable for large-scale grid applications. This is where a lot of the research is pushing. We start with sodium sulfur, and then we move to lithium ion. Lithium ion is still what's in most consumer electronics, and now we're moving to vanadium redox, which is the use for large-scale grid applications. It's more scalable than any of the others. And of course, we have zinc bromine, which is the lower cost battery, which has a low cost, long cycle life, and it uses zinc and bromine. So different advantages and disadvantages. Lithium ion, very energy dense. It's ideal for space-constrained installations like you have in phones or car batteries. If you need a car battery or if you need a Tesla battery, it has very fast charge dispatch cycles and a low self-discharge rate, so you have a lower loss in the upcycling, downcycling. And then you have sodium sulfur, which has a higher energy capacity for large-scale applications, a long-term duration energy storage of 6 to 8 hours or more. Nickel-cadmium batteries, which are durable and reliable under harsh conditions. Long cycle life, ideal for remote applications. And then you have vanadium redox batteries. Again, this is where a lot of the work is coming in. Independent scaling of power and energy capacity, and an excellent cycle life with minimal degradation. That really, you like these because they scale and they discharge very well. Then we have zinc bromine flow batteries, which are cost effective for large scale deployments and are highly safe because they're not flammable. So here's an anatomy of a battery energy storage system. I was giving a presentation one time talking about energy storage system, and someone asked what they look like. And he was imagining like big batteries like a Duracell set up by each other. And actually, it's just different rows and rows of these like bricks of lithium-ion batteries right now. Of course, you can long-term you'll have vanadium redox, and you have 8 specs to keep these things cool. And then you have DC disconnect checks that allows the system to be disconnected remotely or manually when needed. One of the benefits of battery energy storage systems is that they can have black start capability. So there are a few resources that can just turn on and off, but battery energy storage systems are one of them. And that allows it to provide ancillary services to the grid. And then, of course, you have hydrogen fuel cells. These convert hydrogen and oxygen into electricity, heat, and water, offering an emissions-free source of electric power. That's not exactly true. There are some emissions you have to negate, but it definitely doesn't have carbon, and the emissions are pretty small. Hydrogen reacts with oxygen in the fuel cell, producing electricity through an electrochemical process. And then the advantages, you have high energy density for long duration storage in various applications, backup power and transportation. You have scalability and modularity for distribution energy systems. Hydrogen production is very energy intensive and can have emissions unless produced from renewable sources. So, you might say, this is great, why not just produce hydrogen? Because hydrogen burns cleanly, and you can store it, so it removes the intermittency problem. And you can produce hydrogen directly from anywhere you're generating electricity, and you can use hydrogen in a natural gas generator. So you can just put hydrogen in a natural gas generator by outfitting the natural gas generator for hydrogen. And you can store and transport hydrogen with careful handling and infrastructure. You can transport hydrogen, which kind of makes an alternative to transmission networks. So it acts as both storage and it acts as transport. But the problem here is hydrogen has really low efficiency. You will lose a lot of power when you store energy in hydrogen. And also it's, it's just doesn't make sense when it's being used to use it as storage, and you have to produce it cleanly using some renewables, or else it's just as dirty and it has no point. So you don't want to produce hydrogen using natural gas. You want to produce hydrogen using solar and then transport it somewhere else and burn it in a natural gas plant as a way of dealing with the intermittency problem. So co-location, almost all new renewable energy projects involve co-location, and co-location energy storage systems are situated with renewable energy. Why do you think they do this? Why would they put these things together? The answer is smoothing. Energy storage systems prevent penalties in day-ahead markets. They allow battery energy storage systems to smooth over the natural differences between expected and actual supply. They allow for arbitrage. Maybe the renewable energy system doesn't want to take advantage of low price supplies. They want to supply electricity to the grid when prices are high. This allows it to take advantage of price fluctuations and may even buy energy through the energy storage system if there's a big enough price dispersion, lower prices and higher prices in the future, that the energy storage system now opts kind of like an option contract So I'm working on a project right now to model energy storage systems, and we're modeling it very similar to the way you saw option contracts modeled in Lecture 9. Of course, you have stability, co-location to prevent further curtailment and make quick startup and shutdown less likely. Things to consider, and yes, as modeling when you're modeling an energy storage system. Energy storage is about reliability, but it's also about arbitrage. Renewable energy dislikes price volatility. Energy storage loves it. So renewable energy wants to protect against price volatility. Energy storage takes advantage of that. Energy storage would like volatile prices. Renewable doesn't, and this is why you co-locate them together, because they have opposite desires. Up cycles and down cycles can depreciate a battery, so the more you're using a battery, the less valuable it is, and the quicker it's going to become unusable. So you have to consider that when you're thinking about the cost of running a battery. Energy storage is fundamentally a dynamic problem in many ways like option or bond pricing, where you're thinking about the difference between price today and price tomorrow. So think about the BAPM, and if you watch the lecture, think about Black-Scholes. That's kind of how you price this sort of thing. That's how you think about this sort of thing. You are making a bet about the difference between prices today and tomorrow, like you would in an option. And it's a dynamic problem where you're having to store electricity and save it across time. Energy storage is capital intensive with a trade-off between capacity, having enough capacity, and having to have too much capacity and not being able to be efficient because you overinvest in capacity. Energy storage systems are major participants in reserve capacity and ancillary services markets. A lot of the revenue from energy storage does not come from participating directly in the market. And really it couldn't, because you'd need massive amounts of arbitrage, which just aren't there. Because remember, energy storage systems intrinsically have a loss, so there needs to be pretty large price dispersion across time for energy storage to make sense. So modeling dynamic storage choices. So you try to maximize the profit by choosing the optimal discharge and charge cycles in response to market prices. You have a state variable, which is the state of charge at time 2. You constrain it by capacity, and the price of charge and the price of discharge and you obviously submit a bid because this is bidding. So you choose some bid at which you'll buy power and some bid at which you'll choose power. And then the storage tomorrow is equal to storage today plus this new, which is the efficiency factor. You have some loss in storing each period. So new times the amount you charge minus the amount you discharge divided by new. And then there's an upcycling and a downcycling efficiency factor, and then your capacity constraint. You can't store more than the maximum capacity. Capacity constraints are important, and then you optimize these bids across time periods to respond to price forecasts and the state of charge. It's a dynamic model fundamentally. We're going to finish up this lecture next time with electricity market derivatives. I hope you have a great day, and I'll see you next time.